In this video, I'm going to be talking about binomial coefficients, more specifically about the binomial theorem and Pascal's triangle. What is the binomial theorem? It is a theorem that generalizes the formula that a plus b square is a square plus 2ab plus b square. You can have a formula for a plus b to the n, and the formula is k is equal to 0 to n, and choose k. I'm going to do a to the n minus k, b to the k. The reason it's called binomial theorem is because you are adding two terms. So when you have two terms, use the prefix by. Okay, and let's just see that this is in fact a generalization. So in the case when, let's start with 1, why not? When you have n is equal to 1, you get a plus b to the 1 is summation k equals 0 to 1. K, a to the n minus k, b to the k. So I'll start with k equals 0. So that's 1. Oh, sorry, n is 1. So when k is 0, I get 1 choose 0, a to the 1, b to the 0, plus 1 choose 1, a to the 0, b to the 1, and that's just a plus b. So all we are saying is it's tautology that a plus b is a plus b. When you go to n equals 2, you get a plus b square is summation k equals 0 to 2, 2 choose k, a to the n minus, a to the 2 minus k, b to the k, and that then is 2 choose 0 times a square plus 2 choose 1 times a times b plus 2 choose 2 times a to the 0 times b square. And if you just compute these numbers, you'll get a square plus 2ab plus b square. So this is the formula that we all know, that a plus b square is a square plus 2a plus b square. When you go to n equals 3, you start getting new results. So just one last example. Okay, so we get a formula for a plus b cubed, and that is a cubed plus 3a square b plus 3ab square plus b cubed. And this last one, this one was something that was in the homework, and you can see that this gives a to the 4 plus 4a square b plus 6, sorry, a cube b plus 6a square b square plus 4 cube plus b to the 4. So there are two ways of proving the binomial theorem. The first proof goes by induction. And this is long, but the idea is you start with the base case. The base case is n equals 1. And you can see for n equals 1, you get a plus b equals a plus b. Then you assume that the binomial theorem is true for n equals k. And then you try to prove it for n equals k plus 1. You don't need the strong form of induction. You can just do this by regular induction. The second proof is more interesting and uses combinatorics. And this is an example for combinatorial proof. And as we've been doing with combinatorics proofs in the previous videos, I will just do an example to illustrate the idea. So let's see what is happening for a plus b cubed. So say I don't know the formula for a plus b cubed, then I'll just expand this out. Let's multiply I'm going to start with the last two brackets. Let's multiply the last two. Then I'll get a times a plus a times b plus b times a plus b times b. So I'm expanding, I'm unfolding the brackets, the multiplication, but I am not simplifying my results. This is by now a recurring pattern in almost everything we've done in combinatorics. It's actually not beneficial to simplify everything right away because it hides the patterns. Right now you can see some pattern going on here. Now let's expand this out, this unfoil this. Now the first observation we can make is that every term in there has three components. So either there are three A's or two A's and a B, or one A and two B's, or three B's. So the possible, when you multiply things out and you write things as powers, the possible expressions I'm going to get are A cubed, A square B, AB square, and B cubed. What we need to figure out is what are the coefficients in front of these terms. And here's where combinatorics comes in. Let's look at A square B. Where will A square B, where are the terms A square B in here? So any term which has two A's and one B is going to be a term that gives me A square B. So that's A times B here, A times B times A, and finally B times A times A. So these three give me A square B, and there's no other term. So hence the coefficient here should be 3. And similarly for AB square, I'm getting this term, and then this term. And so again, the coefficient is 3. And for B cube, I only get this. And for A cube, I only get that. So both of these have coefficients 1 in front of them. We don't usually write 1 in polynomials. We just leave it empty, and it means that the coefficient there is 1. Claim that this 3 that we are seeing is actually 3 choose 1. Why? Well, what we are doing is we are looking at 3 empty blanks, and we are asking how many ways are there for me to choose a place for B. So I can put a B here, I can put a B here, and I can put a B here, and then the rest will be A's. And you can see that this term is that, this term is that, and finally this term is, oh, sorry, I had here the B should be in the first place. And then I have A, and this term is right here. Okay, so that's why I'm getting 3 choose 1, which is the number of ways of choosing a spot for one B from 3 blank spots. Okay, so that's why the coefficient of A square B is 3 choose 1. Similarly, the coefficient of AB square is going to be 3 choose 2, because I'm deciding where to put the two B's in the 3 blank spots. The coefficient here is 3 choose 0, 3 choose 3, which is the same, and the coefficient here is 3 choose 0, which is 1. More generally, in the expansion of A plus B to the n, the coefficient of A to the n minus k, B to the k, is the number of ways of choosing k spots for B from a total of n blank spots. And the number of ways of choosing k spots out of n is exactly n choose k, and hence the coefficient of A to the n minus k times B to the k is n choose k. So this is an example of a combinatorial proof, and it proves the binomial theorem. Of course, there are many combinatorial proofs, and they prove many interesting results. But we are just skimming the surface, so we will leave this. We will leave this topic at this point. All right. The next thing we want to do is Pascal's triangle. Pascal's triangle is a fun topic, something that you should know since you know what n choose k, what these coefficients are. Okay, so let's start with the result. So first thing is we have an identity which says that n choose k is n minus 1 choose k plus n minus 1 choose k minus 1. Okay, so yeah, there's nothing more to say. N choose k is n minus 1 choose k plus n minus 1 choose k minus 1. I don't think this identity has a name. Now, again, there are two ways of proving this. The first proof is algebraic, where you just expand out and see that the right-hand side equals the left-hand side. Let me just do this so that you can see how you manipulate factorials in equations. So let's say I'll start with the right-hand side. That is n minus 1 choose k plus n minus 1 choose k minus 1. Okay, now I'll take things common. In the numerator, it's very easy to see that n factorial is common in both terms. In the denominator, you have to be careful. K factorial is bigger than k minus 1 factorial. K minus 1 factorial divides k factorial. So I'll do this. And then n minus k minus 1 is smaller than n minus k. So I will do that. And now what I'm left inside is 1 over k plus 1 over n minus k. And now I just combine the two fractions. Here, one of the k's cancels. And then I'll distribute the terms slightly so that I get a nice result. So I'll keep the numerator as that. But then in the denominator, I'll move the k to the front. I get this. And now notice that the numerator is n factorial, the denominator is k factorial times n minus k factorial, which is exactly n choose k. And then that completes the proof. I need to write a few more words, but right now I'm just trying to give you a sketch. So that's the algebraic way of proving these kinds of identities. And these are usually like messy proofs, but if you understand, if you're comfortable with algebra, they always give you the right answer. But now here's the more fun way of proving this result. So this is an example of what is called a combinatorial proof, similar to what we saw above for binomial identity. So we want to show that n choose k is n choose n minus 1 choose k plus n minus 1 choose k minus 1. Now I'm going to interpret both the left hand side and the right hand side as counting something, and I'll show that they are counting the same thing. So if two numbers are counting the same thing, then the two numbers must be the same. Okay, so n choose k is ways of choosing k distinguish k balls out of n distinguishable balls. Okay, so if I have n balls and I want to pick k of them, I have exactly n choose way of doing that. Okay, now suppose we have one special ball. Now I can break the problem into two cases. Case one is that the special ball is picked. So if I pick the special ball, now how many ways are there for me to pick the remaining balls? I'm still picking k total, and I've picked one. So I need to pick k minus 1 out of the remaining n minus 1 balls. And that number is n minus 1 choose k minus 1. So that's the answer for case 1. And case 2 is the special ball is not picked. And in this case, I need to pick k balls out of the remaining n minus 1 balls. And in this case, the number will be n choose k. N minus 1 choose k. But now these two cases are exhaustive. That is, either I have picked the special ball or I don't pick the special ball. So the total number should be the sum of these two. And so the total number of ways of picking, number of ways of picking k balls out of a total of n balls is n minus 1 choose k minus 1 plus n minus 1 choose k. But we also know that this number is n choose k, and so but now using this combinatorial identity, we can compute the n choose k numbers very quickly, and this is something that can be done using something called the Pascal's triangle. So remember, let me rewrite the identity. The identity is that n choose k is n minus 1 choose k plus n minus 1 choose k minus 1. All right, so I'll just show you what it is and then I'll explain what's happening. So you draw a triangle as follows. So first you have these ones. They just come along for the right. So I'll start with the second row and I'll take the two ones and I'll add them, and that will produce 2. Then I'll take the 1 and the 2, I'll add them, and then I'll take the 2 and the 1 and I'll add them, and that will produce 3 and 3. Then I'll take the 1 and the 3 and add them, the 3 and the 3 I'll add them, and then the 3 and the 1. So that produces 4, 6, 4. And then I'll do this. And this gives me 5, 10, 10, 5, and so on. So the triangle keeps on growing. It's an infinitely long triangle. Okay, so all I'm doing is I take two terms, I add them, and I put them, I put the sum below them in the middle. And I do this for every adjacent pairs of numbers. So that's how you form the Pascal's triangle. Now I'm going to remove all these messy arrows in the middle so that we can look at these numbers more clearly. And if you notice, what we have here is we have exactly the binomial coefficients. So let me quickly scroll back up and let's focus on this row. The numbers here are 1, 4, 6, 4, 1. And if you go back up, you will see that these numbers are here, 1, 4, 6, 4, 1. For a plus b cubed, we had 1, 3, 3, 1, and that is exactly this row, 1, 3, 3, 1. So what we are seeing by this procedure is we are producing all the coefficients n choose k. This is a triangle whose entries are exactly the n choose k. And why is that the case? It's exactly because of this identity that n choose k is n minus 1 choose k plus n minus 1 choose k minus 1. So let's see why it's happening. So let me first write down that this row is 1 choose I, where I goes from 0 to 1. Then this row is 2 choose I. This row is 3 choose I. Or I'll use k because I've been using k in the previous. 1 choose k, 2 choose k, 3 choose k, 4 choose k. And then this one is 5 choose k, just so that we are very clear about what I mean by this. The first entry is 5 choose 0. The second entry is 5 choose 1. The third entry is 5 choose 2. Fourth entry is 5 choose 3. Entry is 5 choose 4. And sixth entry is 5 choose 5. Okay, and now let's see why this is working. So if I focus on the fifth row, I'm looking at the third entry. This is 5 choose 2. Then 5 choose 2 is, by that formula, 5 choose 2 is 4 choose 2 plus 4 choose 1, n minus 1 plus k minus 1. And where are these numbers? 4 choose 2 is 6, and 4 choose 1 is 4. And so that's why 10 is 4 plus 6. So it's taking the above numbers and adding them together. Let's do just quickly one more. Let's pick this entry. Then this is 3 choose 0, 3 choose 1, 3 choose 2. And by that formula, 3 choose 2 should be 2 choose 2 plus 2 choose 1. And let's see where these things are. So this is 3 choose 2, then 2 choose 1 is that, and 2 choose 2 is that. And so Pascal's triangle and this identity gives us a way of finding these n choose k terms by doing addition instead of multiplication.